Here we discuss how to compute the stream function and show how it satisfies the definition that we described earlier. So assume that we have a flow field which is incompressible and two-dimensional. So it's a vector field U, and we assume that we are in Cartesian coordinate. So we have two components in the x and the y direction. Then we define the stream function is a function such that the partial of psi with respect to x is equal to minus the y component of the velocity field, and the partial of psi with respect to y is equal to the x component, so u, of the velocity field. So this here, if you have a two-dimensional incompressible flow field, these are the formulas that you need to use to compute the stream function. Alright, so this is here what you need to know if you want to compute the stream function, but in the following what I will discuss is how can you explain that this formula give you a stream function. So remember earlier we said a stream function is a function such that the contour of the functions correspond to streamlines. So imagine this is our velocity field, and let's see, so one streamline here might look like this. I'm trying to draw a line which is always tangent to the local velocity vector. So this here might be a streamline. And so a stream function here, if that was a stream function associated with this vector field, then along this streamline I would have that psi of x and y is equal to a constant for every single streamline. So for this one as well. All right, so that would be for constant 1. This one would also be a contour. This streamline would also be a contour. Of course, the constant might be different. But so this is the definition. This is how we want to build our stream function. So here, let's assume we want to build this stream function. Now, the first requirement is therefore that our function is constant along a streamline. Now, one other way of saying that is that the value of the function psi doesn't change, or that d psi, the differential along a streamline, is equal to 0. So we have d psi equals to 0 along a streamline. Now remember the formula for the total differential. Psi is a function of two independent variables, so d psi is equal to partial d psi partial dx times the differential of x plus partial psi partial y times dy. This is again the total differential of psi. When I'm writing this, I'm assuming that x and y are independent variable, and what we want is that along a streamline, so if we are no longer now moving along a random dx and dy, but if we're actually moving along a streamline, that the change in psi is going to be equal to 0. So what we want is as d psi equals partial psi partial x dx plus partial psi partial y dy. We want that this is equal to 0 if dx and dy are no longer independent, of course, but if the value of the function here, the value of our function shouldn't change if our dx and dy is moving along a streamline. So that means if dx dy is parallel to the local velocity vector, and therefore that has to be parallel to uv. So one way of writing that these two vectors, even though this is not really a vector, but that these two are parallel, is to say that the cross product is equal to 0. So dx dy cross uv equals 0, and so that we can write as dx times v minus dy times u is equal to 0. And from there we can see that dy and dx are no longer independent variable, right? So we cannot pick dy and dx randomly. If we say we're moving along a streamline, we have to have dy, which is equal to v divided by u times dx. Okay, so our function needs to be constructed such that psi will be a stream function, provided that d psi, which is equal to d partial psi partial x times dx plus partial psi partial y times dy, which along a streamline needs to be v divided by u dx, v divided by u dx, if this is equal to 0. Right, so we can factorize the dx. So partial psi partial x plus v divided by partial psi partial y dx is equal to 0, and that is equal to 0, of course, if this here is equal to 0. So that's our first requirement. This, if we have this relationship between the partial of psi with respect to x and the partial of psi with respect to y, then if this function exists, it will be constant along a streamline. This is our first requirement. Okay, and our second requirement is simple. You see here that we are going to define a function based on its partial derivatives, and if psi is a function of two variables, then the partial derivative, partial psi partial x and partial psi partial y, need to satisfy the following equation that you may remember from your multivariable calculus. The cross derivative have to be equal, otherwise you cannot define psi as a function. So we need the partial with respect to x of the partial of psi with respect to y to be equal to the partial with respect to y of the partial of psi with respect to x. The cross derivative terms have to be equal to 0. This is a mathematical requirement for this function psi to exist. Right, so we have one requirement which, if psi satisfies this, if the partial of psi satisfy this conditions, that the function psi can exist, and we have one requirement which states that the function psi is going to be constant along a streamline of the vector field uv. And so the only thing we have to do now is to verify that our definition for the stream function satisfy these two requirements. So remember, we define our stream function such that psi partial x, we will compute our definition using these formulas. Partial psi partial x is equal to minus v, and partial psi partial y is equal to u. Okay, so the question is this psi a stream function? Right, so let's see if it satisfies the first requirement. So our first requirement is that partial psi times partial psi partial x, which is minus v here, Right, so minus v plus v divided by u times partial psi partial y, which we define as u times u. Right, this is indeed equal to minus v plus v, so this is equal to 0. Check. Let's look at our second requirement. We need the cross derivatives to be equal. Let's start with the first one. What is the second partial of x? Sorry, partial x of partial psi partial y. This is equal to partial x of partial psi partial y, and partial psi partial y is u. So this term is equal to partial u partial x, and the second cross derivative is equal to the partial with respect to y of partial psi partial x. Right, so this is equal to minus v. So one cross derivative is equal to partial u partial x, and the second cross derivative is equal to minus partial v partial y. And then the question is, are these two equal to each other? Right, so those are the cross derivative of these two equal to each other, and the answer is yes, provided the flow is incompressible. Right, given that the flow is incompressible, it satisfies the continuity equation or the compressibility condition, partial u partial x plus partial v partial y equals 0, and therefore these two are equal. Therefore partial u partial x is equal to minus partial v partial y, and therefore the cross derivatives are also equal. Check. So this is the reason why you can only define this, these formulas here will only define a stream function if you have an incompressible flow, because otherwise you cannot satisfy this second requirement.